Thank you very much. I thank the organizers for the nice opportunity of talking in this very nice workshop. So as the title suggests, I will talk about two things, secant varieties and interpolation, but mainly actually I will talk about interpolation. So I will start by recalling the definition of secant variety. I will spend a few words to tell you how to translate the problem of computing dimensions of secant varieties to certain projective varieties that we have seen in this workshop into some interpolation problem. Then we will mainly discuss interpolation, more general interpolation problems. And at the very end of the talk, we will see how secant varieties naturally show up again when doing interpolation. So maybe the structure of my talk is the following. I start with secant varieties, and then we go along a loop talking about interpolation. And then we come back again to secant varieties at the end. So just to see how these objects, geometric objects, are very well connected. So let me start by, well, writing once again the definition of secant variety. We all know it, but mainly I want to fix my notation. So if X is a non-degenerate projective variety embedded in some projective space, P capital N, by non-degenerate I mean that it doesn't live in a hyperplane. So it fills, the linear span fills up the whole space. What is the secant variety? I like this notation, sigma S of X. This is defined to be the elements, the points Q in the ambient space Pn that lives in a S minus 1 projective space in the span of S distinct points, P1 and Ps, with Pi distinct points of X. But then I also want to take limits of this S minus 1 place, so I take the Zariski closure. In terms of tensors or rank of tensors, these are the elements in Pn with border rank at most S. So what are the varieties? Well, this is a general definition, but actually we focus on some particular examples. So what are the fundamental varieties for this talk? Well, first of all, the Segre variety. X can be a Segre variety. So this would correspond to tensors like Q, tensors in a tensor space, A1 tensor, tensor AN. So these are Segre varieties, but also we will consider Veronese varieties. And these correspond to symmetric tensors, so polynomials. Symmetric. But I can also combine these two objects and take Segre embeddings of products of Veronese varieties. So these are the so-called Segre Veronese varieties, and these, in terms of tensors, they correspond to skew-symmetric, partially symmetric tensors. And what is the main question that we are going to address is to compute the dimension of the secant variety to this kind of projective varieties. So the main question that we are going to discuss is computing the dimension of sigma S of X, where X is in this list. Well, what is the main tool that one uses in order to try and answer this kind of question? This has been discussed already in the tutorials on Monday morning. It's Terracini lemma. So I'm now, actually, as I promised, I'm now translating this problem into an interpolation problem using Terracini lemma. So what does Terracini lemma say? Well, in the same notation as above, X is a non-degenerate projective variety in a projective space. Then I take a point Q in the sigma S of X, a general point. So Q lives in the span of S points of X. So Pi in X. So if I want to take, well, if I want to compute the dimension of this variety, I might as well take a smooth point and compute the dimension of the tangent space to that variety at that point. That's the same number. So this is the object that I'm interested in, the tangent space to the secant varieties at the point Q. Well, Terracini lemma states that this is equal to the linear span of the tangent spaces to the variety X at the given points P1 and Ps. Tx P1, Tx Pn, Ps. So when one wants to compute this dimension, he can compute the dimension of this linear span. So for instance, if I take the twisted cubic, something like this lives in P3. This is the third Veronese embedding of the projective line, by the way. So if I want to take a point Q on the secant variety, I'm taking a point on a line. And so I want to compute the tangent space to this point Q, at this point Q to the variety. Well, what I do is I take the tangent lines, maybe I should use colors, the tangent lines to the points P1 and P2, and I just compute the linear span of these lines. And this by Terracini lemma is going to be my object. So I can take this line and this other line, which is Q, and they will span a P3. Well, they will actually span the entire space. So this proves that the secant variety, this variety of secant lines to the twisted cubic is indeed the whole space. So that's a pictorial proof of this fact. But of course, one can do this in general. But let's continue. We didn't get to the linear system setting yet, so let's do that now. So let's L, curly L be the line bundle that embeds X, my variety X, in my projective space Pn. So something for which I write this embedding. Then I take the projectivization of the global section X0, XL. I guess I should take some star somewhere. Well, that's my Pn. So let's fix a line bundle that gives me this map. And in my examples, Segre Veronese and Segre Veronese variety, that's very easy to see who this bundle is actually. So in the case of Segre, so the Segre embedding of P and 1 times P and R, the line bundle that I'm considering is O of 1, 1, 1. Yeah. So it's a line bundle of multi-degree 1, 1, 1, 1 on the product of projective spaces. In the case of Veronese, I take the dth Veronese embedding of the nth projective space. Then the line bundle that I have to take in order to get this embedding is O of Pn d. So I just take the structure sheaf and I twist it by d. That's what I get. And in the case of Segre Veronese, well, that's very easy to figure out by looking at these two examples. In the case of Segre Veronese, I just take L to be, it has to be a multi-degree line bundle, and now I'm adding, instead of ones, I take degrees. That's the Veronese part of this embedding. So that's, I just write d1, dr. I think r was the number of factors. Okay, so having said so, when I have this line bundle, now I want to understand how to relate it to the dimensionality problem for secant varieties. So the point is that there exists a bijection between the hyperplanes. This follows from Terracini lemma, the hyperplanes of Pn containing the tangent space to the secant variety at the given point. This is in correspondence with elements of the following bundle. So I take L, and I twist it by the ideal sheaf of S double points. The points are the one that I'm taking, so P lives on the span of S points, and then I just take the power 2. So I just take this I, let me denote it, P1 square PS square. So who are these guys? Well, for instance, in the case of the Veronese, so L is given by, basically is the vector space of homogeneous polynomials of degree D in n+1 variables, and when I twist it by this, I'm just asking that I'm just taking those who actually vanish with multiplicity 2 at the given points. So that's an interpolation problem, because now I'm asking who is the space of polynomials of degree D vanishing with multiplicity 2 at a given collection of points. Well, this correspondence follows from Terracini lemma, and basically this is they are orthogonal to each other, because this the tangent space to x at pi contains the derivation that will kill my polynomial f in order to say it interpolates that point with multiplicity 2. And then I take all of them, I have s points, and I take all of them, and that's how I get this correspondence.
Elements of?
Sorry?
What do you mean when you say elements of?
Well, that's, okay, so this is a linear system, but I can think of it, this is a line bundle, but I can consider the corresponding linear system, and I can think of it as a vector space. In the case of Veronese, for instance, I can think of it as a vector space of homogeneous polynomials of degree D, where D is the order of the Veronese embedding in Pn. So hypersurfaces of Pn.
It's up to scalar.
Yeah. And then if I want to consider, well, the Segre Veronese, then this will be polynomials with multi-degree D1, Dr. And then again, I'm imposing the vanishing of partial derivatives, all partial first order.
I just was wondering how you're right. I mean, literally, a hyperplane does not correspond to a point in the total space of a bundle. That's
Sections of that.
Yeah, section of that. Yeah. The H0 of that. I mean, sections of that. Yeah, I'm abusing notation. So this tells me that, well, the codimension, this correspondence tells me that the codimension of the sigma S of X, well, keep in mind that X is one of these three guys. Of course, one can do the same, taking any hyperplane sections of any variety and then imposing double points, but this is what we are interested in, studying Segre Veronese and Segre Veronese varieties. So this tells me that the codimension of the secant is equal to the dimension of that linear system. So this is equal to dimension of L twisted by V1S, sorry, 2. So that's how I translate my dimensionality problem for secant varieties to a dimensionality problem for linear systems. So this is an interpolation problem with double points. And actually all classification results or even partial results about dimensions of secant varieties to these kind of objects have been proved by means of this correspondence. So all the results, as far as I know, all the results have been translated, these problems have been translated into interpolation problems on double points and solved in that setting, and then you get the dimension of the secant variety. And let me list what is known so far about this. So, well, the most celebrated result is the so-called Alexander and Dershowitz theorem. This deals with Veronese varieties, so they completely classify secant varieties to Veronese varieties, and the way they do is they completely solve the interpolation problem for hypersurfaces of the projective space with any collection of general points. These points are in general positions. Maybe I forgot to say it. So they completely, well, I'm going to write this when the classification is complete. So I'm not going to, so they prove that the dimension is always the one that you would expect, except in a finite list of cases that I'm not going to write now. There's another, concerning Segre varieties, there's another complete result due to Catalizano, Geramita, and Gimigliano. Emiliano. Well, this dates back to the 90s, actually, Alexander and Dershowitz. Then later on, there were simplified and shorter proofs. The original proof is 150 pages long, or something like this. And then it was simplified by many other authors. But another, now talking about, maybe just write Veronese. By Veronese, I mean interpolation problem in PN. And then another complete result is by Catalizano, Geramita, and Emiliano in 2011. And they completely classify Segre embedding of products of projective lines, so any number of factors, but all of them P1s. This is also solved now, again, in terms of postulation of double points, of interpolation on double points. So though all cases are non-defective but one, I think with four factors. Okay, thank you. And then this was for Veronese, this is for Segre. 4 different Segre, so with bigger spaces, there's a conjecture. You can find the conjecture on a paper by Abbott, Aviani, and Peterson, but that's still open. I mean, maybe there are some partial results, but it's still not known. So exceptional cases are known, but the difficult part is to prove that all the other cases are non-exceptional. But what about...
Cross PM is no.
Yeah, indeed, yes. For the two factors is no. They are all three factors is known. Segre.
Right.
Okay.
Factors that have all the same dimension.
Okay. All the same dimensions. Okay.
That's Strassen.
That's of course. Yeah. But PA cross PB cross PC, this is still not known.
Mostly understood.
Yeah. Anyway.
This is the one that we did in Macaulay 2, the first, right? This is what we computed some PA cross
Yes.
PC. The first step.
Yeah, I think it was P1, P2, I don't. Yeah, low cases, of course. I mean, all these proofs are done by induction. So by induction on the degree, in the case of Veronese, and on the dimension, and by induction on the number of factors in this case. So when you want to do induction, you need to know the initial steps first. And it's always very useful to use a computer like Macaulay do to just solve all these cases by hand, and also to get like an intuitive idea of how it's going to be later on with higher parameters. But let me just briefly continue this. This is just an historical, let's say, overview, but this is not exactly what I'm going to talk about. So in the case of Segre Veronese, there are also few results known in the case of 2 factors. So there are a couple of papers by, I think, Ballico, Alessandra, and Catalizano. They classify all these cases, P1 cross Pn, with by degree, any by degree. So this is also completely classified. And also, again, Alessandra, Enrico, who was here last week, Carlini, and Catalizano, again, they gave some partial classification for the case of Pn times Pm, but with by degree 1 and something, and this is partial. It's not completely solved. In the 3-factor case, there's a work by Hiro and Chiara Brambilla. They recently found new defective cases in this setting for Segre Veronese. New defective cases. But a complete classification is far from being known. Another complete result is about Segre Veronese embedding of products of projective lines, P1 cross P1, any number of factors. This is also, and any multi-degree P1 dr. And this this is due to Laface and myself. That's also a complete result, and also in this case we did it by studying postulation of double points on products of projective lines. Okay, but yeah, so I guess in the list of exercises that I proposed for the problem sessions, I gave some particular cases of this. Yeah, now I don't remember. I think I asked to compute the dimensions of the secant varieties using Macaulay 2 of P2 times P2 times P2, and Segre Veronese of P2 times P2 with a given pi degree. I think it was 2, I don't know. But anyway, when the parameters are low, like in these cases that I'm mentioning, of course, you can solve it by Macaulay 2. And that's why we are here. So, okay, so this is, as I said, all of these were solved by means of postulation of double points. But what about generalizing in this direction? So forgetting the secant variety setting for the moment, and instead trying to solve interpolation problems for higher multiplicities. So can we do that? Can we? Yes, we can, and that's what I'm going to talk about in this talk.
Can you just say, before we erase the center board, just give the example of the 2 double points, why it comes out in this case, just for the sake of people who haven't seen it before? Good.
Which example?
Yeah, I mean, so this correspondence in the bijection, in the case of the twisted cubic, why is it that Terracini's lemma says that you need 2 double points?
Well, yeah, so...
Make it explicit for the graduate students is what I'm saying, because I know not everybody has seen this bijection.
Yeah, okay, so the point, now I'm not even sure I'm able to write down the details, but the point is that you fix a point on the cubic, on the twisted cubic, and that's a polynomial, that's a monomial, that's the power of a linear form of degree D in degree 3 actually in 2 variables, and then you want to take the tangent space to it. So basically it's given by, so if L to the 3 is my element on C3, that's the twisted cubic in P3, then if you want to consider the tangent space at that point, I might as well just write it. Then this is given by monomials of the form L to the 2 times G, some other stuff. And then you want to do it for more points, like for instance for 2 points in this case, and then you ask who are the. So if you go into the dual coordinate ring, so you take the ring of derivations, then you ask who are the derivations who kill my. So you have to take first order derivatives in order to understand the tangent space. And taking first order derivatives means imposing a double point, so asking that my polynomial of such degree in such variables vanish with multiplicity 2 at a given point. So not only it has to vanish at the point, but also its first order partial derivatives have to. Okay, so and then of course we can, as I was saying, generalize this construction and ask for higher multiplicities. So I'm asking that not only the first order partial derivatives vanish at my given point, but all partial derivatives up to a given number that I can fix. So higher multiplicity. Okay, so what I'm doing now, well, now I stick to the Veronese case. So actually I'm taking Pn. So now I take Pn and I fix integers d, m1, ms, and I make sure that d is bigger than all of the other integers. These are natural number. And then this is going to be the degree, and these are going to be the multiplicities at a collection of s points. So I take P1, Ps in Pn, general points in general position. So I don't want 3 of them on a line, I don't want 6 of them on a conic, and so on. They have to be general. And I introduce this notation L to be depending on all of these parameters and d m1 up to ms. So I'm writing L and d m1 ms. So this is my object of study, and this is just the vector space of homogeneous. So we work over C. of the complex numbers, we want to consider all homogeneous polynomials of degree d in n plus 1 variables. They will give me a hypersurface of Pn. That's such that if I take the derivative of order, any derivative of order mi minus 1, and I evaluate of f, and I evaluate it at the point pi, this is 0 for all I. From 1 to s. So what I'm saying is that, okay, I take my homogeneous polynomial of degree d and I ask that it vanishes at the point. Well, actually, I'm asking that the m minus 1 derivatives vanish at the point, but that's enough. I mean, because this is homogeneous, so that's enough, considering the highest order of derivation. If I want to take the affine version, then I have one less variable, and then I need to ask for the previous derivatives. But that's, we stay with the homogeneous notation, so that's enough. And the question is, how many of these polynomials do I have? So what is the dimension of L? Well, there's a naive answer that is just given by a parameter count, because of course I know exactly how many polynomials of this degree in this number of variables I have, and I know exactly how many derivations I'm imposing. So this is a linear system of equations in the coefficients of my polynomial, so I can easily count how many of these polynomials should survive after this killing with the derivatives. So this actually gives a lower bound to this answer, and that's what we call the virtual dimension, denoted it by the dim of L. That's just the difference between the number of homogeneous polynomials of degree d, n plus d choose n, minus, and then for every point I want that all the derivations of order mi minus 1 vanish. So how many conditions do I have? N plus mi minus 1 choose n. So this is always less or equal than the actual dimension, because what can happen is that, so if these are linear equations that I'm imposing, that it's a linear system of linear equations, but some of them there may be some relation among them. They may be not linearly independent. In that case, the dimension would be bigger. I would have less conditions. Some of them will be just a linear combination of the previous ones. So this gives me a lower bound. And then I say that if, well, let's just take non-empty objects. So let's assume that there is actually something in this linear system, that there exists some polynomial satisfying this interpolation condition. I say if the dimension is strictly bigger than the expected dimension, then I say that L is special, defective. So when the conditions are not linearly independent. And what I want to do in this talk is to actually compute the speciality, so compute the difference between these two numbers. So let me just call it H1. I'm going to briefly say why I use this notation for the difference between dim of L and virtual dimension of L. Why do I take H1? Well, it's because I use algebraic geometry in order to prove it. So that's actually the dimension of the first cohomology of my linear system. So the point is that, but I'm not going to go into details. I just want to justify this notation that is not completely crazy. Well, it may be, but so the point is that what I want to do is to blow up my projective space in my points. So I consider P the blow up at P1 PS of Pn. On Pn, I have this linear system given by this formula, and then I just take the pullback of it. So I take the strict transform of element inside there, and it turns out that the Euler characteristic of this is actually equal to the virtual dimension. It is exactly, one can prove that it is exactly that number. It's not very difficult. But one can also prove that, well, this is the alternating sum of the dimensions of the cohomology groups. But one can also prove that only H0 and H1 are important. All the higher cohomology vanish for free. So just please accept it. That's not difficult to prove. So the virtual dimension is the difference between the H0 and the H1. But what is the H0? Well, that's just the dimension. It's the dimension of this linear system seen as vector space, as cohomology. Yeah, so the speciality is H1. That's why I call it like this. But let's proceed with some examples, because what I'm going to do is to, rather than proving non-speciality results, I'm going to prove speciality results. So I'm interested in the special cases. So let's just start by seeing some of them. So for instance, in P2, so in the plane, so I'm considering linear series of curves, and I fix a degree. I just take the first non-trivial one, 2. I take conics, planar conics, and then I fix 2 points, 2 distinct points with both of them multiplicity 2. So, well, I can use my formula, my naive parameter count, and say what is the virtual dimension of this guy. So what is the expected dimension? What do I expect it to be? How big it is? So this number is 0, because I have in total 6 conics in P2, and then each double point will give me 3. It's point plus the 2 tangent directions. So these are the 3 derivatives. So that's 0. It's 6 minus 3 minus 3 is 0. But actually, so if I draw 2 points, distinct points in the plane, then I can consider the line connecting them. And then I can just use Bézout theorem to see what is the intersection number between this line and a general conic in my let's just write L, intersection with L, where L is this line, and I get -2. That's just Bézout. So this tells me that the line is, the line is contained. I get a negative number. So the line is contained, and it's contained with multiplicity 2. So actually, so what does it mean? That there do exist a conic which is singular in 2 double points. This conic is singular along the whole line. It's the double line. That's a conic. A double line is a conic. It's singular along the whole line, in particular at the 2 points. So this is an element in my linear system. So this proves that the dimension of L is actually 1, but it was supposed to be 0. So the speciality is 1. But, okay, so you can say, okay, this is kind of a very easy example. Does this happen also for higher degree? Do I get this line, just a configuration like this? Yes. Let's see this other example. I take degree 6 sextics in the plane, and I take points and 1. Again, I take 2 points with multiplicity 4, so I can compute the virtual dimension. This is going to be 8. That's just an easy parameter count. But let's think about it a little bit. So I have 2 points in the plane, and I want to consider a sextic which has multiplicity 4. I again do the same trick as before, and it turns out that the double line, not only the line, but the line twice, has to split off the system. It has to be contained in all of the elements like this. So an element, a sextic inside here, is not irreducible. It is the reduced union of a double line and something else. And something else that looks like this. So a quadric, so the degree was 6, I remove a double line, I get degree 4, and it has to go through the points twice more. So this is, so the dimension of L is equal to the dimension of the linear system of quartics, with 2 double points, and that has dimension 9. So again, I get that the dimension is not what I expected. The H1 is again 1, but I have again a double line. So is it always the case that whenever I have a double line that splits off the system, it will give me a speciality which is equal to 1? Yeah, it is.
It says it's at least 1, but it could be even bigger.
Yes. In this, it is at least 1. It could be even bigger, but it will be 1. Okay, but I can also, what about other curves? Now we get a line that splits off. What about I get other different curves that split off my system? And that's also a famous example. So I take degree 4 in P2, I take quartics in P2 with 5 double points. And again, I do the parameter count and I get that I should be empty. I should not have such a quartic. But we all know that if I fix 5 general points, these points are in general position. Well, yes, they are not 3 of them on a line. So we all know that through 5 points, general points of P2, I always have a conic that looks like this. But then I can take the double conic, and that's something of degree 4, which is singular everywhere. In particular, it is singular at the 6 points, 5. So that's again an element inside here. So the dimension is actually 1. I do have one element. I do have one polynomial that satisfies my interpolation conditions. And again, I get speciality equal to 1, exactly as for the line. So it seems that whenever I have a curve which is twice doubly contained in the base locus, or it's fixed with multiplicity 2 in the base, it's a fixed component of multiplicity 2 of my linear system, it seems that it creates troubles. And how to quantify these troubles, it seems to be exactly 1. So the question is it this, at least in the planar case, is this the answer to can this help somehow to answer the interpolation problem, to explain the speciality of linear systems? Well,
can I ask you, if
yeah.
I understand your example, so in an example of D equals 6, then you're saying that the sec6, which have 2 points that are fat, like 4, multiplicity 4, is actually a different variety. It's a variety of quartics with double points to union another variety of lines. And saying there, so like these varieties become every time.
Maybe your section.
Maybe.
No,
It's not, well, I mean,
it's just a thing of things that look like that. That's
the way to.
Variety of quartics that satisfy, or sec6 that satisfy that property is actually the variety of sec6 that split.
Yeah, it's not a variety, it's linear system. So the point is that you write all the sextics have to be written like 2 times the line plus L prime, where L prime is the linear system of quartics with 2 double points. And they have to be the same, they have the same dimension, and that's how you compute it. That's it. So we have seen that whenever you have a curve, a rational curve with higher multiplicity high enough in the base locus, then this will give me H1. And actually, in general, it's easy to prove that, well, easy, I mean, one can prove that if there exists a rational curve, let's call it C contained in P2, such that the intersection number with my linear system is at most -2, like it was in the cases, it was exactly -2. And moreover, well, I also require that the normal bundle, let's just a technical, let's move on. That's just a technical extra condition. I wanted to have the same normal bundle as a line. But I wanted to say that one can see that whenever there's a curve behaving like this, then the linear system L is special. This is the easy. It's not easy, but one can handle it. But the point is that there's a conjecture, a well-known conjecture due to Segre, Harborn, Gimigliano, and Dershowitz. Segre, Harborn, Gimigliano, and Dershowitz. I'm sure I'm misspelling some name. Anyway, so they conjecture that that's actually an if and only if. So whenever a system is special, it's because of the presence of such a curve in the base locus. And this is known to be true in some cases, but it's still open in general. So this conjecture is known to be true whenever I have at most 9 points. And this Nagata, Gimigliano, Harborn. yeah, series of work by these three authors show that this is actually.
So in that case, you can get a rational cubic then.
Sorry?
You get a rational cubic in one of those when S is large, like a same domain.
Rational cubics should not create speciality, but
That's
it,
the normal condition.
yes, that's a normal condition.
So that would say you probably only get quadrants of Conex on one.
And then, so one setting under which this is true is when you bound the number of points, but then you let the multiplicity be as high as you want. But also it's true for every number of points and bounded multiplicity, 12, I think. And this was proved more recently by Ciliberto and Miranda. And they used a very complicated degeneration argument, and that was, to prove that this conjecture is true up to multiplicity 12. Otherwise, it's open. But of course, one can use Macaulay too and find some nice examples and instances where the conjecture is true. But, okay. But so far we have talked, I introduced the problem in full generality, so here we were in Pn, but we only talked about the planar case. What I'm actually going to do now is to move to the higher dimensional case. So not only we will see lines splitting off my system, but we will see higher dimensional subvariety that will create speciality. And we want to try to describe them, at least detect who they are and try to understand how much they contribute to the speciality. So that's our main next task. So the idea, let's say the plan is to do the following. First of all, we need to understand the base locus of L, because in higher dimension I will see curves, but I will also see bigger, higher dimensional stuff. So I cannot talk about fixed components; these are not divisors. There will be like any possible dimension between 1 and codimension 1. But then, so I want to understand who is actually in the base locus of a given inner system. And I want to understand which of the cycles of the base locus actually create speciality. So identify components of BSL that produce speciality, and these are what we call special effect varieties. This terminology was introduced by Bocci in his PhD thesis. Also abstractions. And this, I guess, was introduced by Chandler. Well, anyway, these are objects that are in the base locus, but they are in the base locus with multiplicity high enough in order to give H1, such as the double line and the double conic. The single line is in the base locus, but is not special effect. The double line is. Same for the conic. And then, third is compute H1. So why do we get exactly 1 for a double line? Okay, so this is the plan. And let's start with the easier case. So let's consider the linear base locus. So let's consider the cycles of the base locus, which are linear subspaces of my projective space Pn. So I'm going to talk about linear special effect varieties. Linear special effect, such as the line there. And this is joined with Maria Chiara Brambilla and Olivia Dumitrescu. So first of all, we want to give a base locus lemma. So let's fix an index set I1, IR plus 1. So we want to identify who are I mean, here we saw the line, but of course, if I have more points in a bigger space, I can take a plane spanned by 3 points, a P3 given by 4 points. These points are in general position, so they will always span a full dimensional projective space inside the big projective space. So let me parameterize these spaces, these objects. So I take I and a multi-index that is contained in 1S. So I'm just choosing R plus 1 of my points. And I will introduce this number K of I to be, well, I take the sum of the MIs, the sum of the multiplicities of my points that are parameterized by this set I that I fixed, minus RD. So I fix this number. I will explain why I get this number, but I'll take this number and then, okay. And then lemma, base locus lemma. That's the first thing that we have to do. If Ki is bigger or equal than 1, if this number turns out to be positive, then the linear subspace Li, which is just the linear span of Pi with I in I. Okay, so if I have 2 points, this is a line. If I have 3 points, this is a plane. P3, and this is L1, 2, 3. That's a plane. So if this number is positive, this plane is contained, or this linear cycle is contained in the base locus of L with multiplicity. Yeah, let me write at least Ki. Well, if R is 1, I'm just taking 2 points, and that's exactly the intersection formula here. M1 plus M2 minus D. This is what you get here. And then, of course, you can use induction and iterate this Bézout problem, this Bézout theorem, in order to get the same corresponding number for like a plane, for instance. Because now if I have a plane, I have 3 points, I want to understand what is the multiplicity of containment of that planes, then I just first of all take a line. I know by Bézout I can intersect a line with a hypersurface and I get a number, right? So this will tell me the multiplicity of containment of the line. But then if I want to consider the whole plane, then I just take a point on that line and the other point. And so if I already know this line and I ask what is the multiplicity of the plane, now I take this extra point and I take the line connecting that point with a point on the line. Of course, the union of all these planes, of all these lines, will give me my plane. So by iterating what I said before, I can compute the multiplicity of containment of this dashed line, and this is going to be the multiplicity of containment of my plane, and you get this formula. So it's not very difficult. That's how it is. So this is the first task. So we know that whenever this number is positive, that corresponding linear cycle is contained with at least that multiplicity. But then, yeah, that was one point. But then, which of them are actually special effect for my linear system? For instance, the line was special effect only when K, the corresponding Ki was at least 2. So in general, this is the same for higher dimension. So whenever Ki is the dimension of the cycle plus 1, so 2 in the case of a line, 3 in the case of a plane, this is special effect. Li is special effect. So not only it is in the base locus, but it also produces H1, speciality. And the third thing is to see how much it produces. I mean, what is the H1 that it gives? So it contributes to the H1 by, and then I'm going to write a formula, minus 1 to the R plus 1 times n plus Ki minus R minus 1, choose n. Here is its contribution. So in the case of a double line, this is a positive sign, and this would be a 2. So you would have n plus 2 minus 2, choose n, 1. And that's exactly what we got. But then you can do the same for higher dimension. I mean, this is the formula that you get. So if the line is more multiple, it will give more multiplicity, more a speciality, and if the and the same for higher dimensional stuff. And then you have a plus minus thing depending on the dimension. On the dimension, so this yields a new definition, a new lower bound, well, a new definition of expected dimension. This is what we call linear expected dimension. For my linear system, it follows from this base locus lemma, because I know that whenever this is satisfied, and in particular whenever this number is big enough, I know that my system is special. And I can now also compute how much special it is with this number. So I can give a new formula for the expected dimension, which is just the old one plus the sum. Let me call this L of I, this number that I get, and then I just take the sum over all i's, over all linear subspaces. And that's let's see an example. Yes?
I'm very sorry. Could you recall what was R? It was
R is just a number of points that I'm taking. So R is here. So I just fix R plus 1 points. I do this trick for computing the multiplicity of containment. So I iterate Bezout. It's an induction argument. I know it for lines because I can intersect a line with a hypersurface. And then I can... if I know it for the line, I also know it for this line, so I know it for the whole plane, and so on. So this is something that turns out to be true in the proof. Let's say that you have to have this number big enough, but you see it, right? Because if this number ki was smaller, then this would just be 0. So this number you actually get by means of restricting. So the point is that I'm not doing it now, but the point is that I said at the beginning that to study this interpolation problem and in order to use algebraic geometry, one should blow up the space in the points. But now, if you want to deal with linear cycles, you also want to blow up these linear cycles. And this turns out to be like some cohomology of when you restrict your divisor to your linear system to. It doesn't make sense. I don't want to talk about it, but that's just how it is. So let's, I'm just going to show you an example, and then I want to move to some more interesting abstractions. So for instance, in the case of cubics of P3 with 3 triple points, so the virtual dimension, one does the computation and is negative, is minus 10. But we know that if I have 3 points in P3, and then I can consider the plane. I'm going to draw the plane like a triangular, as I did. This reminds a little bit of the polytope of a P2 in toric geometry. So the plane spanned by the 3 points, one can see with this formula that it's going to be contained with multiplicity 3. So actually, if I take that plane 3 times, this is an element. It has degree 3, and it has multiplicity 3 at the 3 vertices. So actually, this shows that the dimension is 1. So I have to justify an H1 equal to 11. So how do I do it? Well, I use this formula. So every line, so I have 3 lines. Each of them is with multiplicity 3. So that formula gives me a 4. So this gives me 3 times 4. 4 is what you get from this number. And then I have one plane with multiplicity also 3. And from this formula I get minus 1. And this is 12 minus 1, 11. That's what I wanted to get. Yeah, so, well, let me just briefly, our theorem proves that this formula is actually true, so the dimension is actually equal to this. So all the special effects varieties are actually these linear cycles whenever S. So the above is true, meaning that the dimension is equal to the linear virtual dimension, that is this number, so meaning that all the special effects are linear, if, well, whenever S is at most n plus 2, and under some bound when S is more than n plus 2, so it's at least n plus 3. And this bound, it's something that makes sure that, it's something that ensures that there are no rational normal curves in the base locus. We saw that conics are rational normal curves in the plane. They may give speciality. So if I avoid them by bounding the multiplicities in order to see no rational normal curve, I can prove this. So I'll go back in a few minutes to the rational normal curve case, so let's just forget it. Yes, so let's just forget it for the time being and done. Okay, so the point is that up to n plus 2, the problem is completely understood, and in particular, it has some nice connection with the theory of moduli spaces of stable rational curves with, I have to write n plus 3 to stay with my notation. So the point is that Kapranov identified this moduli space with the blow up of the projective space Pn at n plus 2 points, all the lines connecting the points, all the planes, and so on. So these are my linear cycles. So somehow divisors in my setting here in the blown up space are elements on the Cox ring of this. So that's a connection with some, other geometric problem. And then from n plus 3 and on, you don't have this correspondence anymore, and things become more difficult because of the rational normal curves. So I will talk about this really, really briefly. So the point is that rational normal curves, because I also promised that I was going back to the secant varieties. So I'm going to write rational normal curve, and their secants are special effect. So let me just remind that that's a Castelnuovo theorem, that there always exists a rational normal curve, unique, a rational normal curve through n plus 3 general points in Vn. So I know how to find a rational normal curve that passes through my points. And then I can give a base locus lemma in the same fashion as for the linear stuff, for the rational normal curve, so I can compute the multiplicity of containment. Let's for the time, that it's just some number. I have no time now to explain it, but I know that it exists. I can just use intersection theory to see how many times it will cut my hypersurface. And then I can give the same, I can go on like this and see when this is going to give me H1. But I'm going to illustrate this in an example. I think that's easier. So you have to be big enough in order to, your dimension has to be big enough in order to see this phenomenon. So, well, one first example we saw in the first blackboard, because when we saw the quartics in P2 with 5 double points, we got this conic that was a rational normal curve through 5.5 is the magic number for P2. So we got that, and that was a special effect. But this will be reproduced in higher dimension. This phenomenon always occurs. So let's consider 9 points of multiplicity 6 in P6, and I consider degree 8. So, well, I know, well, here there are plenty of lines and so on, because the multiplicity are big enough in order to satisfy this condition. So there are plenty of linear stuff, but we know them already. So instead of writing virtual dimension, I just write linear virtual dimension, because this is something that we know already, that we already know how to deal with. So this number is minus 147, but one can actually compute that there exists one element inside there. I don't think you can do it by computer. This is too big. But for sure you can do it by algebraic geometry. You just take birational transformations of Pn into some some other, what we call Cremona transformation, and you can reduce this linear system to something smaller for which you can actually compute the dimension. I'm not going to show how I compute this, just believe me. But we have to justify quite a big number here that is not given by linear stuff, because this is already counted. So when one can use Bézout theorem to see how much the rational normal curve that passes through the 9 points is contained in the base locus, and it's contained with multiplicity 6. Just believe me. I mean, it's just a intersection number formula. So it's very natural to think that it contributes like a line. So that's also a rational curve. So I'm gonna use this formula. So if it is contained with multiplicity exactly 6, then I can use this formula to see how much it contributes. And the contribution is given by 10 choose 6, which is 210. It's pretty too much, because now I have minus 147 plus 210. I have to get to 0. I have to go back. I need some negative number. But the point is that, okay, so I have my rational normal curve. Let me just represent it by this. It's in P6. And I know that it is contained with multiplicity 6. So now I take a point, like just fix, for instance, my point P1, one of my base points, and then I take any point Q on my rational normal curve, and then I can use my base locus lemma for linear stuff, so I can use my base locus lemma for lines in order to compute the multiplicity of containments of this line. So I just take a point on the curve, which is one of the ones I fixed, and then I take any other point on the curve, and this is going to be contained with multiplicity. There's 6 plus 6 minus 8 is again 4. Yeah, so it's again 4. But then I can move my point Q all along the curve. And by doing this, I just take all these lines with fixed P1 and all the lines going along the curve. So what I get is a cone. It's a cone with vertex P1 over my rational normal curve. So it's the join of P1 with C. And the join is the union of these lines which are contained with multiplicity 4. But that's a surface. So I got a surface which is contained with multiplicity 4. So if I use the formula for the plane, and I believe that this formula is actually good also for that, then I get a negative number, and I get minus 7. But I have 9 of them, because I only took P1. I can take all the other points. So I actually now, all cones, I obtain minus 7 times 9. So just putting together all the numbers I have LDIM plus 210 minus 9 times 7, and this is 0. So yet I didn't solve my problem. I have to get to 1. So there's something else. But the point is that, and here secant varieties show up, the point is that what is the secant variety to the rational normal curve? Is the union of all of lines given by 2 points on the curve. So what if I take Q and Q1 and Q2? These are not my base points. These are extra points. And I can still, so I know that each of them is contained with multiplicity 6 because the whole curve is. So if I take the line connecting them, then it's going to be contained with multiplicity again 4. And if I take the secant, that's union of all of these lines, and that's a threefold. So now I obtain that the sigma 2 of the rational normal curve is contained with multiplicity 4. So I go back to this formula, I get a plus something that is exactly 1. And this completely explains my problem. So in general, well, this was just an example, but the thing that we are working on now is rational normal curves and their secants, and also joins between curve and line. In this case, it was a point, but I can take the join between the curve and a line and something else. And these turn all out to be special effect varieties. So we believe that we can solve the problem for n plus 3 we have a conjectural formula. That's the obvious one. By looking at the example, is the same as that, and we believe that this is true. And I just wanted to conclude by saying that, of course, one can use Macaulay too and solve a lot of examples at the beginning and actually test that our conjecture is true, and then use induction. Thank you. That's it. Sorry for.
Maybe just a quick question.
Yeah, sorry for running over time.
No, this last example I think is really new.
Yeah.
Nobody studied before this behavior, so I would like to, if you can say just one word more. These are 6 points in
P6.
In P6. So this is sigma 2.
Sorry, 9 points in P6.
P6.
The sigma 2 is a triple in P6.
Is the responsible of the defectivity for the hypersurface of the V8.
Yes.
In P6. So okay.
And also you can go on and take higher secants. So now if you take the 3 secants, so the variety of secant planes, and you do the same trick, you can compute the you do have a base locus lemma for that. It follows from the linear one. So you can compute this number, and multiplicity of containment of the 3 secant, which is a 5-dimensional, it's a 5-fold. It's contained twice, and that's actually the only one element inside here. The 3 secant has degree 4. And it has multiplicity 3 along my points. So the sigma 3 is this linear system, degree 4 and 3 to the 9. And if I take it twice, I exactly obtain this. And you can get it from this computation. And I really believe that this is just an example. Then that's how it works for n plus 3 points. I didn't write it. That's a work in progress again with Chiara Brambilla and Olivia Dumitrescu.
Cool. Well, since we're short on time,
sorry for